Okay, thank you everyone for coming. This is part of a faculty position interview for the AI position. And I'm going to pass it on to our colleague to make introductions.
Hi everyone, we are very glad today to invite Dr. Donald to give us a research seminar. His area is in computer vision. Dr. Donald is a postdoc researcher in UCLA. He has his PhD in applied math and computational science in Tufts University. And he has a bachelor degree in mathematics at Shanghai Jiaotong University. It's an honored degree. His research focuses on developing computer vision models that minimize human supervision. He is also interested in the robustness of AI models, computational imaging, and optimization. Don's work has been published in top-tier vision and AI journals like CVPR, ICCV, NeuroIPS, ICML, and etc. So you're very welcome today here to give us a talk. Thank you.
Thanks for having me. Yeah, my name is Deng Lao. I'm a postdoc from the UCLA-Vision lab. So it's my great honor and pleasure to be here. And from the title, you can see there are two keywords: bootstrapping perception. Perception is easier to understand. It means analyzing the surrounding environment from sensory input. But what about bootstrapping? Bootstrapping is about the process that we develop such an ability to perceive. And in the development of our own vision system, I would assume that there is no external annotation for us. Nobody has told us, hey, there's a guy here, there's a television here, right? But we still develop our own vision system. And it is my goal to develop a machine vision system also from the ground up. That is why I am so interested in bootstrapping. So I want to open this talk with, let me see, okay. I want to open this talk with an iconic quotation from the movie Jurassic Park, that is, don't move. He cannot see us if we don't move. So this guy, his name is Alan, he's a scientist. And when they are attacked by the dinosaur, he knows that the dinosaur has a so-called amphibian vision system, which means they cannot see things that don't move. So that's how they are standing here and the dinosaur cannot see them. So we humans have a way more advanced vision system. And that is how we can see them, see these people here, right? We can see the face, even if they are not moving. But, well, I have an example here. So can you see anything? Nothing, right? What about now? Right. You see the logo of LSU here. Sorry for those on Zoom. I think this may not broadcast well on Zoom. Yeah, but so people here will tell you they can see something here. But in case I'm not tricking you, we can pause it at any moment. Let's see. Pause. Look at this. The moment we pause it, the pattern is gone. We can do it again. Let's do it. Let's do it again, right? We pause, it's gone. So how can we see these patterns if the colors are exactly IID? So we only see these patterns by their motion. So I assume this is what the dinosaurs see, but I cannot verify that, but this is what I assume. Yeah. And yeah, so in the process of evolution, how did we get here? From such a primitive vision system to what we are right now. It raises like two very interesting questions. The first one is, how did we develop a perception system from the ground up? And the answer in this question will give us the answer to the second question. That is, how can we build a perception system from the ground up? The first one is telling us how do we get here? The second one is about how can we use the same mechanisms that are there to build a machine vision system. So in year 1964, the godfather of modern neuroscience, Rouge and Baton, they did this experiment on cats. They put a cat in front of the screen and show the cat different patterns and they record the cat's neural response to different patterns. And there is this one particular neuron that they didn't get any response, not until an assistant accidentally knocked the projector and moved things in the screen, and then they record a big pause in the cat's response. Right? Then they realized that cats are very sensitive to certain motion patterns. Why is motion so important? Well, I'll show you a video here, and it's pretty colorful. But if I show you its motion pattern, boom, the object shape is there, very clear. And if I give the same input to computer clustering algorithm here, we get pretty garbage result. But once I give the motion to the same algorithm, we get almost perfect segmentation result for this object, even if this requires zero prior knowledge about this object. We don't need to know what it is. Just by its motion, we can find this object. Now let's take one step back and look at how machine vision is trained these days. So these days there are like tons of like so-called vision foundation models that shows great advancement. Well, so I will show two of them. So the first one, CLEAP, it's a state-of-the-art vision language model which trains on 400 million image and text pairs. What they do is they take the image and map it to a vector, take the text, map it to a vector, and then align them by training the network. And these image text pairs are usually scrapped from social media like Instagram or Twitter. And also this state-of-the-art feature extractor, Dino V2, trains on 140 million images of objects. And what they do is they create different augmentations of the same image and align them. And this is called contrastive learning in computer vision. And there's something in common between them. That is, their data need human input. So it is pretty easy to understand that language requires human input. But what about objects? Why do we need human input if we only need images of objects? So I'll show you the example. This is a tiger. This is actually Mike here. Yeah, Mike the tiger here, right? And what is this? This is also Mike. I went there and I took this photo yesterday. And this is what Mike looks like in real life, right? And so what's the difference? On the left side is what you always see in a textbook in computer vision data sets. And on the right side is the real life, what it looks like. So on the left side, you can see it's at a canonical position, right? It's at the center of the image. I think you know better than me that Mike doesn't always look like this. It's only the photographer who wants to portray Mike, put it in the center of the image and make it look like this. And now you see a gap here. We train our images like A, but we want them to work on images like B in real life, right? So there's a gap here. And so far we talked about two gaps. Let me do a recap. First one is humans do not need external input to find objects, but machines do. This is from the motion, right? And there are other things we can use, but today we'll talk about motion. And the second is we train machine vision models on these images like A, but we expect them to work on real life data like D. So you may ask, hey, if these models work pretty well, then why don't we just give them more data? No longer the case. So this is published in this Dino V2 paper. When they train on 1.4 million images, this is what they get. When they have 10 times more data to train, there's a huge bump in their model performance. And if they have 10 more times more data, well, it looks like the performance saturated. And if we relax the requirement on this object-centric data, like artificial data curation, the performance actually drops. So scaling here already hits a bottleneck. All right, so let's look back to this object. I intentionally keep a gap between now and then we saw it, but I hope you still recognize this object, right? And can anyone tell me what's the name of this object?
Jellyfish, I don't know.
Yeah, kind of like a sea
I'm gonna
slug.
use Google.
Google
Image.
image.
Yeah. Yeah, just for your reference, this is its name in Latin. Yeah. And I'm a scuba diver, so we call it like nudibranch or sea slug. Yeah, so 1 point for the sea slug, right? But you see, no matter what we call it, doesn't change our perception to this object. We can always call it a cow, a car, we can call it Mike, we can call it a rocket. It doesn't change our perception to this object. It's all about attaching a symbol to this object. So what I just walked you through is a bootstrapping process. We start from the raw data. We use low-level vision information to get the samples. And then we develop some abstraction. And the last step is about attaching sample. Well, if there is no sample available, we just give it a name. We can call it Mike, right? Apparently, current vision models are doing very well in this part, right? We've already talked about vision foundation models. And it is my goal to solve this part by bootstrapping. And just look at this chart, right? There's so much data that current vision model cannot digest. So by bootstrapping, if you can make use of such data, there is infinite potential. So of course, there are many mechanisms that we can use in vision. What I just walk you through is using motion. So today I will talk about two of them. One is about finding objects, which is motion, we already talked about. And the other one is understanding spatial relationship, which corresponds to geometric perception of the surrounding scene. So we can navigate around the surrounding thing without bumping into things if we know how far things are from us. So I will talk about them separately. So let's talk about motion first. We talk about like we can get the objects by motion, right? But what does that mean to a machine vision system? Look at me, right? Here the color is white. Here it's black, right? If you have an untrained vision system, how can you tell they belong to the same object? The color histogram is so different, right? But if I start moving around, right, and you will see this white color and this black color, they always move together in the same way. And now you know they belong to the same object. Now what if I take off my jacket, then you will know it also belongs to another object. But the thing is, in this whole process, we don't need to define what a human is or what a jacket is. Right? We can just have this purely data-driven way of finding objects only by their motion. And speaking of motion, we have to define motion. We have two images. And for each image, for each pixel in an image, we can have a vector pointing it to where it is in the next image. So this is the collection of this vector is a 2D vector field, which is something we call optical flow. Just rest assured that there are many ways of estimating optical flow, but that's not the focus of the day. Just make sure that flow can be estimated pretty well these days, and without human supervision. And so with this optical flow, we can establish this correspondence. We can use the current image to reconstruct the next image. So the next image is IT plus 1. So you can see this IT and warp by the optical flow, warp the coordinate system, and then we can map it to the next image, of course, with some ID random Gaussian noise. And just for your reference, this is called Lagrangian reflectance model in computer vision. I have a visual example for this warping process. We can see that we can warp the first image to the second image by this vector field. And you may notice that there is something wrong with the tail of the car. So what happened here? Does anyone know what happened here?
Like a mirage.
It looks like, well, so in the first frame, this piece of information is not available, right? It's occluded by this car, so it's occlusion over there, and that's why it triggers some of these interpolation artifact. Yeah, I think some people call it mirage, or like some people call it like ghost effect, something like this, right? But it's occlusion. But we will talk about occlusion later. All right, so now it is my goal to generalize the model to a video. Now we have a sequence of images. We have a collection of objects which maps to each image, and each object has its mapping to the image, so it's the motion. And then we want to know where the objects are in each image. And by the same logic, we can have this energy function to minimize, right? So we're no longer reconstructing the image by the last frame, but we're reconstructing them by the objects F and their motion, the warping W. And of course, I will sum over all the objects and over all the images in the temporal frame. But so far, we even have not defined what these objects are, what these Fs are, right? So usually these Fs are 3D objects, so they map to the image. But mapping 3D, measuring things in 3D is really expensive. So instead, we want them to be in 2D, and this is what we want. Just look at the F in the middle. You can see both the head of the car and the tail of the car, right, in the same image. So it looks like the car, like it's like opened up version, like 2D version of the 3D car, and this is exactly what we want. And only a portion of the object maps to each image. So to solve this system, there are three things to answer. F, the object, R is where the objects are in the image, and the motion, W. But motion here, if we define the objects in 2D, then it's a 2D to 2D mapping, so we can solve it by optical flow. And so F and R. It takes some math to solve, so we're not going into any derivations, but just to give you some keywords, because we measure things in continuum, so we need like variational calculus, we need the Euler-Langmuir equation to derive the functional gradient descent. This is just for your reference. It's not important to the result. And let's look at the result. So if I have a rotating blob here, the layer or this like 2D model is just like a opening up map of this rotating Earth, right? So this answer has an explicit solution or closed form solution, which is the aggregation of the visible part of this object from different frames, right? That's why how you see it opens up like a map. But for the segmentation, not so lucky, we don't have an explicit solution. And that's why we run this gradient descent on the boundary, on the contour that is defining this object. And this is how we run gradient descent. So here are some results. You can see we find these objects from the videos only by their motion. We don't have to tell the model, hey, there's a car over there. What a car is, there are 4 wheels. No, we don't have to, only by their motion, without any human supervision, without any human symbolic priors. And so we talk about occlusion. So having this model, occlusion is easily addressed. We can just map what we have to the spatial temporal host to address occlusion. For example, in the bottom left is the input to the algorithm where there's a video and there's a human defined mask given by the user. So you can see this human is in the red color, right? And we can just map the background to this thing and then remove it from the video. And this is called in-painting in computer vision. And if we want, we can even remove the shadow, right? So we can do automated object in-painting just by doing segmentation and object removal altogether. So this is fully automated.
So this won't work on any object that's not moving, correct?
Yeah, so this is essentially addressing moving objects.
Okay.
Yeah, when there's something not moving, then it requires inductive learning, means we need to guess what is there. Yeah, but this is for motion and removing objects by that is moving. Yeah. And some interesting thing is we can create these very fancy vision filters here, just for the maybe social media. Right? This is just show off. This is so this whole video doesn't need any human prior, doesn't need any reliance on like knowing what the object is. Right? This is pretty good. And another thing I want to emphasize is we can also resolve the ordering of the depth of the things. Depth means the distance between the objects to us. So we can just resolve the depth, the ordering of the depth by inferring their occlusion relationships. We already talked about occlusion. So knowing if one is occluding the other one, we know it's closer to the camera. This is very intuitive, right? So this model can also resolve such kind of depth prior. Yeah.
I assume that's like a relative depth.
Yeah. It's not the absolute one. Yeah, the ordering. That's why we say the ordering of the depth. Yeah.
What if the object that's moving has more degrees of freedom? Like they move, like after some time it moves in a different dimension.
Oh yeah,
like,
yeah. So this is it, right? So we have this rotation here, right? For example, this one is triggering this self-occlusion. And for a reference, this is the only model we have right now that can handle this kind of motion, right? Usually what they do is just one occluding another, so they do like 2D planar motion, and this is the only model that generalizes to 3D motion.
Does it become more difficult when you have multiple moving objects at the same time?
Yeah, for sure. Yeah, but so before this model, people have to solve a combinatorial problem because one occluding other, there are it's a combinatorial relation, right? There are a lot of like, so the hypothesis space goes up by exponentially by the with respect to the number of objects. But this one we're disentangling this from the ordering of the depth. So we solve for motion first, and then in the end we resolve depth. So it becomes linear. So
but I'm thinking if you have like two objects that are moving at the same time and they collide, are there going to be any issues with that?
No, not at all.
Okay.
Yeah. So
because the moving objects are going to be overlapping.
Yeah. So that's why I'm here, this one, right? So we have multiple objects here. Like the cars are moving, right? There are multiple cars, there are multiple objects here, and then not an issue.
So you only need to segment the moving things, but you don't need to identify which is which, right? That
No,
is like
no, I don't have to. Yeah. So, all right. So this pretty much concludes this layer work, and but there's still something that is preventing us from using it on large-scale training. That is its efficiency, because it requires iterative optimization. It processes a whole video batch, and it is sensitive to the initialization of these contours, for example. Now let's look at how human vision works. Our visual system receives data sequentially, and we make decisions, we process it in real time. So the next work I'm going to talk about is how we can keep the same principle for the moving objects, but we use deep learning to modernize it to make it fast. So here's what we do. This is the video. Instead of using a whole video, we just take the instantaneous motion, which is the motion between two frames. And now, instead of allocating them into different layers, we use a deep neural network to encode them into a series of latent codes. So a series of slots. So each slot corresponds to one layer, and each slot is just like a 1/48 vector, just for your reference. And from each slot, we can decode only a portion of this input motion field. And the combination of them will reconstruct the whole input. And so this network can be trained by this reconstruction loss. And in this process, we can get the segmentation mask automatically from this reconstruction. And just for your reference, this is called the slot attention network that was introduced in year 2020 by one of my collaborators. But there are two issues with this network. This is a good starting point, but there are two issues. The first issue is, what if one slot is too strong? The representation capacity is too big. What will happen is one slot will be good enough to reconstruct the whole input. Just think about it, right? If one slot is like long enough, big enough, then they can reconstruct the whole input. So there will be issue with like separation between the regions. And the second issue is, what if one slot is too small, it's too weak? Well, real objects in real life have very complex shapes. So as you see here, and the 1/48 vector is not likely to represent all the shapes we can have in the world, right? So these are the two challenges we try to tackle to make this thing work. For the first challenge, what we do is, in addition to the original decoder, we add one more branch, the adversarial decoder, to these slots. And the adversarial decoder does is, it does not only decode this motion in each specific region, but it tries to decode the motion in the whole input, like image domain. Look at this, right? On the left side, we're decoding things in the whole image domain. And on the right side, we're only decoding things within each region. So then we add this loss to it. And what this does is, the original decoder is trying to fool the adversarial decoder, trying to make sure that it cannot reconstruct things well outside its own mask. So it looks like these two networks are wrestling with each other. That's why we call it adversarial decoder. So one aims to reconstruct everything, one aims to fool the other one outside of its mask. In this case, each slot can only encode information within each corresponding region, which leads to separation. And well, the second issue is complex shape. Yes. So let's zoom in a decoder. This is a standard convolutional decoder. What we do is we give it an image as an input to the decoder, so that the decoder can use the image, use the prior information, use the statistics in the image to help with this reconstruction. For example, here, the edges in the image align very well with this motion boundary, right? So we can use this piece of image information to help with reconstruction of motion, so that we can reconstruct the very complex shapes from very basic latent code. And these are just some technical details, so I'll just show you the ablations. Here's the image. If you give it to the original slot attention model, the image is too colorful and the model doesn't get much. Well, if you give the motion to the same model and train it a little bit, right? Looks like the model already captures where the objects are, but the results are not very accurate. Now, if we give it a conditional decoder, now you see the objects are aligning with the image, the objects in the image, right? And in the end, if we give the divided attention model, if we give the adversarial decoder, we get the objects. So this is the ablation for this work. And here are some results. On the left side, it was the original slot attention model, which was trained on these like toy examples. and only works on this kind of like artificial examples. And on the right-hand side, once we have our model with motion, it can really work on real examples. And remember that all these output here are obtained without any human supervision, without any human input of what objects I want to get. They are only extracted by their motion. And now we have the state-of-art performance, and it's definitely real time. And if we compare this, so this is the only model right now that can find arbitrarily different number of moving objects. But even if we compare it with like older models that only finds, let's say, one object through this binary classification, the model is still faster and more accurate. So this is how strong this model is. And now we can go back to bootstrapping because we have this raw video data. Now we have this model that can extract these objects only by their motion. Remember the goal in the very beginning, how we can identify things only by their motion? Now we have a model that we can find this object. And now we can give these objects to these vision foundation models to learn. And what is different is we don't need human. We just need to find these objects by their motion. And we did some like preliminary result experiments where we give it 5,000 very random videos on the left side, which doesn't have any artificial data curation. We didn't prepare these videos. We just randomly found 5,000 videos from some random data set. And we found like 200K objects. Just by training the same foundation model, we had like 15% performance improvement just by this bootstrapping process. So this tells us like what we can do only using motion without any human requirement.
15% or 115?
Oh, it's like 115. It's it's 15% over the original. Yeah. So yeah, this pretty much concludes the part of the motion. And there are some additional references about like the work we did about motion.
So when I talk about bootstrapping, you mean just to get the specific region of that image with?
Yeah. So we extract the objects. So
like a mask.
Yeah. So we can find objects like this. So on the right-hand side, so for each object, we can just create a bounding box around it.
Right.
And then we get these samples, but without any human annotation.
And then for downstreaming, you just use the mask for training or?
Yeah, we just use this map for training. Instead of using the raw data for training, we got 15% bound. Yeah, please.
I was wondering if you could just give a little bit more information about the architecture of the slot attention network.
Sorry?
I was wondering if you could give a little bit more detail about the architecture of the slot attention.
Oh, yeah. So this is the network architecture. Here it is. Yeah. So the input is 2D. It can be image, can be motion. Here I use motion, and it encodes them into different slots. Each slot. So for a reference, it's a transformer architecture. So each slot is a token. And at the test time, we can just add more token or remove more token. So this network can handle arbitrarily different number of objects without like retraining them. Just add more token or remove more.
Thank you.
Just one question following this. So in this case, you are say one slot or one token just reconstruct to part of the image.
Yes.
And you have on the other slide that adversarial decoder that construct the whole
image. Yes.
So how do you actually enforce that the decoder, the regular decoder, only reconstruct a part of the image?
Oh yes. So this is because the original decoder outputs 3 channels. So the adversary decoder outputs 2 channels, which is the motion direction. And the original decoder gives us the motion direction, which is U hat here, and also M, which is a mask. So now we use this mask to mask this reconstructed motion. So the reconstruction is the point-wise multiplication.
So it's the decoder itself that says here is the
exactly
the region that
exactly.
The other part I don't care. Right?
Yeah.
Thank you.
Yeah, thanks for the question. Right. So so this pretty much concludes this motion part of this talk. And we have some other work on like finding objects with minimum algorithm latency, and we generalize them to generic objects. And also remember this aggregation scheme we have, that rotating Earth thing, right? So we can use the aggregation, very similar aggregation scheme for computational imaging, where we can remove the turbulent air, the air turbulence just by aggregation. So we had a paper this year in CVPR, and it's highlighted. But yeah, this is just additional reference. And now let's move from motion to geometric understanding of the scene. And yeah, so we need to understand the geometry. Just some recap. We need to understand the geometry of the scene to move around the scene to avoid bumping into things. So it's in our instinct. And the task we are interested in is called depth estimation, which estimating the distance between points in the scene to the sensor, like our eyes or camera, right? So we human are equipped with this hardware to estimate depth. That is our eyes, right? If we have two eyes, not if, we have two eyes, right? And so we can do this triangulation to find where the objects are, right? So we have a very good solution once we can find correspondence. And for your reference, this is the equation to compute it, where x minus x prime is the offset. So what the offset means, just cover one eye and cover the other eye. You will see that there's a slight misalignment between what you see, right? And this x minus x prime is that. So this equation is pretty straightforward. If the offset is bigger, which means the object is closer to us, the d is smaller, right? And if x minus x prime, vice versa, right? And for reference, this special case of the epipolar geometry in computer vision. And but now here's something interesting. If we have only one input, one image, molecular input, how can we guess how far things are from us? So how far are these cars from us? Can anyone just answer?
The eyes to see, so it's hard.
Yeah, just do you have any rough estimation how far the cars are from us?
Like,
First one.
Yeah.
like 4 feet.
5 meters, 10 meters, maybe, yeah.
Like
Well, now?
which car?
Oh.
Yeah,
Oh,
well,
the white card. It's the white card.
Yeah.
Like
Yeah,
2
it
meters.
doesn't matter. Anyway, you're gonna get it wrong, right? Yeah, so now how far it is. And when I was giving this talk to someone else, someone said, hey, the cars are 10 meters from us, and it's just the head is so big. I was like, yes, you are totally right. And that is why this problem is so ill-posed. Because different things can result in the same image in our eyes or in the sensor, right? So now, and so to estimate the distance, it requires our priors on this object, requires to draw the information from our prior experience, which requires learning, and it's called inductive learning. And for machine vision, it requires learning from a training set. So binocular vision doesn't require any supervision, just by triangulation. But the monocular vision that requires supervision, now it gives us a very unique opportunity to supervise the monocular vision by this binocular vision. Right, so on the left side, we have 3 annotations. And additionally, depth can also be estimated by other methods, like a direct measurement, for example, just use a LiDAR or a depth camera. So I think our cell phone all has a depth camera on it, right, to measure how far things are. Or they can just be estimated from videos without any supervision, just by establishing correspondence. So essentially, depth can come for free. And here's a depth map, probably I would say it's a bedroom. And here's the semantic map of the same bedroom. And can you see any similarities between these two maps? Looks like the edges align with each other pretty well. They are both like piecewise smooth, right? So we have a question, right? Can we just use these depths to help with downstream semantic understanding in this case? This is just a motivation. So we have this hypothesis. Put pre-training on a geometric task will benefit for downstream semantic tasks. Because nowadays, neural networks are like tens of millions of parameters, and just training the network on a smaller data set is not enough. So it's the de facto choice that people use a different task to pre-train a network, and then load these pre-train weights for the downstream task. So our hypothesis is have pre-train on the geometric task and the test on the downstream semantic task. Yeah. So yeah, it's a very experimental paper, and we have tons of analysis in the paper where we vary data sets, supervision, architecture, compare with different baselines and different fine-tuning strategy, and so on and so forth. In the end, we did over 100 settings and more than 10,000 GPU hours just to validate this hypothesis. And we're pretty happy that the answer is yes, molecular depth does improve downstream semantic segmentation. And as you can see from these curves, the segmentation accuracy is not only more accurate when pre-trained on depth compared with classification or random initialization, and the training loss is also converges faster and the training loss is lower. So this raises the question, why? It looks like classification is a semantic task, right? So we're trying to classify the image into different semantic classes, while depth estimation is a geometric task. So a semantic task should transfer to semantic better than a geometric task, right? But this goes back to human factor. This is a standard, very standard image in ImageNet, and it's labeled as a car. Why it is labeled as a car? It's not because there's only car in it, but it's because a human annotator labels it as a car. There are other things in the image. For example, what about the human in the background? To this task, they are the nuisance factor that has to be discarded, not relevant to this car, right? And but this is geometric inference. We have the input image and we have the output depth, which is a dense prediction task. So the granularity feeds this downstream semantic understanding better. And this is a bootstrapping process, which doesn't require any human involvement, doesn't require any human annotation. Just remember, we can get the supervision for depth for free, right? And so if we visualize the output, we look at where the errors are. And we can see on the right-hand side that the model pre-trained on classification is missing these like tiny little humans, for example, these fine details when compared with model pre-trained on molecular depth, because this piece of information is to be discarded. They don't exist in classification because they don't matter. But for depth, for molecular depth, they really matter, and that is how we get this kind of results. And yeah, so pretty much this concludes the most important result in the paper. And we tried different things, like we vary the training set size for downstream semantic segmentation and to replicate some kind of like few shot learning scenario. And the model pre-trained on molecular depth is always better. This is one. And the other one is, well, we can try different depth supervision. Remember, they come for free, but we can use video, binocular, and LiDAR to supervise depth. And what we found is the better the supervision is, the better the downstream semantic understanding is. For example, LiDAR is direct supervision, it's direct measurement, right? So the downstream semantic is better. And we also tried some different other different like semantic tasks, for example, object detection, and the results are also positive. This is just for your reference. So yes, just for your additional reference, these are some work related to depth that we did. As you imagine that this is the first work that validates the viability of using a geometric task for downstream semantic understanding. So we use this work as a foundation, and we try different ways to improve depth sensing, like range sensing on the left side, or the sensing with language priors. Just remember the car result, right? If I tell you it's a car, then you know how far it is. If I tell you it's a toy car, then you will have a different answer, right? So we have human in the loop here, and with language priors, we also have different works about like enhancing the visual features for better dense prediction tasks, like depth estimation, right? So this pretty much concludes the technical part of this talk. Any questions? Yeah, please.
What is, I like the idea that you have this depth information that help the downstream performance. So what is the trade-off? I want to get an idea of the trade-off. Let's say your downstream performance going from 30% to 35%. The cost is going to be how much what's the amount of the pre-training data you need and how much time you need to train?
Oh, yeah. So,
Resource wise, how many GPUs?
yeah. I see. So this is very hard to answer because nowadays these vision foundational models are trained on tons of data and we cannot compare with them in terms of the scale of depth training. So here we just did something in a similar scale where we take the vision foundation model for downstream for depth estimation to compare with this only model only using like images. So I think the scale is relatively the same scale in terms of amount of data, like in terms of like millions or billions of images. But I forgot what's the detailed number.
Oh, actually,
Yeah.
I wasn't asking about scale. I'm asking about say if I want, let's say I want like 5% improvement.
Yeah.
What is the amount of data or training time I need
Yeah.
in the pre-training stage for that improvement?
Yeah, I think for us to get this thing, so on this experiment, the model pre-trained on classification is on ImageNet. So it's like 1.4 million images. And the depth model we trained is on driving scenes. So it's about 60,000 images, not much, right? And just think about it. If I want to deploy a robot or a car in a self-driving scene, for example, to a new city, all what I need to do is to put the depth sensor in front of the car and just drive around. Let's say like if we drive at like 30 frames per second is like standard sampling rate. Each hour we'll have 100,000 images, training images already there. So data is not too expensive when we collect it for depth because we can get it for free without any human annotation, right? So I hope this answers your question. Yeah.
So here, when you say LiDAR, is that basically using just a camera plus LiDAR data?
Yeah.
Okay.
Yeah.
So
So they match with each other.
So you're getting better rates with LiDAR, right?
Yeah.
Okay.
Yes.
Was the data segmented into different weather conditions?
I don't think so. We just train them all together. Yeah.
Okay.
So I think in the data set we tried, it's mostly there's no ring or something, but this robustness towards the weather conditions is also something that we are interested in.
Because I mean,
Yeah, LiDAR is
it's
sensitive
not very
to
good. It's
panic.
not very good on, yeah.
Yeah.
But there's terahertz radar that's coming out now that's supposed to take care of that.
Yeah. So I think if it rings, LiDAR is okay, but if it snows, LiDAR is really
LiDAR is
bad.
not
Yeah.
good, yeah.
Okay, so we talk about this motion and geometry, right? I hope by now you are convinced that just giving the model more and more data and more annotation will reach a bottleneck, and that is why we are so invested in a bootstrapping method without human involvement. But motion and the geometry is only the tip of the iceberg in the ways we can do bootstrapping, right? We can use occlusion, saliency, localization, manipulation, reconstruction, and prediction, for example. Is for bootstrapping. So we just scratch the surface and it's like a gold mine for us to explore, right? So this leads to the future research direction, which I call going up, going down, and going broader. Going up means upscale. Since we already have these supervision signals explored, why don't we just use them and on a larger scale? For example, we download every single image or every single video from online, just train on it, right? And which is doing large-scale training on generic visual data. We may incorporate large language models for sure, and this requires multi-GPU, multi-node parallel training. And to achieve this, there are two key factors. First of all, we want to be more efficient. So under the same constraint, we can make use of more and more data, which our divided attention model already shows such potential. We train on one single GPU, and it reaches like over 100 frames per second. And the second is to be versatile, means under the same constraint, we should be able to make use more and more different types of data, right? So different data modalities, for example, where we have this ongoing work about using occlusion prediction for generic pre-training, which trains on both videos and images. Well, it has the potential to train on multimodality, and we reduce the GPU memory compared with the Stellar model by 20%. So this is the first direction, going up. And the second direction is going down. So just look at these pandas. They're very cute, right? So they're trying to learn to ride this horse. And they do it by environmental interaction, by trial and error. But so far, there's no machine model that can achieve this. Think about it. This is such a simple task, but what it requires perception, requires actuation, right? Requires a policy, different things, right? So going down, what I mean is embodiment means I want to have an automated training scheme that if I deploy a robot to roam around, the more data it gets, the better it gets, which requires automated learning in embodiment settings, maybe in simulation or in a real robot, and multimodal sensing, which requires 3D perception, for example. And we have this ongoing work about like 3D perception, where we align the features in the 3D space, and we can show that it can improve 2D perception, actually. And also requires sequential data, continuous learning, and human in the loop, which we talk about like having human language in the loop for depth perception can help. Well, human is not needed, but if we have them, it's better, right? And in the end, it's more longer term. It's about once we have the models trained, we want to make use of them to deploy them. So we need to care about that robustness, safety, privacy, and fairness in these AI models. And also managing data beyond just simple perception. For example, healthcare data, right? Material science data, for example, radiation data, right? We have like different things that we can try. And the last step is about interfacing with humans, because once the model is trained, we want them to work with humans, which requires them to be interpretable, and we want to build a system that can do this human-computer interaction. And for this direction, well, we are already like trying to tackle the instabilities in AI training and the robustness towards adversarial perturbations. So just for reference, this is something ongoing. And this pretty much concludes this talk. And here are my collaborators. Some have PhD titles, some are professors, and some are the students that I work with and I mentor. And the work is not possible without their help. And so thank you. Yeah, so on the right-hand side is my cat. So I'm trying to reproduce the visual cortex experiment, you remember that. So put the cat in front of the screen. And I was playing this at home, and my cat is so attracted to this motion pattern. And it sits there and keeps watching it. Yeah. So, yeah, thank you.
So I have a question about the motion-based segmentation.
Yes.
How good is it? Like, are there more unsolved problems that you're facing? For example, like in the slides 20 or something, you had a Jeep moving on the road.
So you're talking about my hidden slide, right?
Oh, no, the slides you showed already. Like, motion-based, like image segmentation, the first part of your talk.
Let me find it.
Where?
Give me a second. So this is
just the car moving, I guess. The car was moving.
a car was moving.
Yeah, I mean, yeah, this one.
Yeah.
So you have a segmented version of that one?
Yeah.
Like a red picnic.
Yeah,
mask,
the red one.
mask.
Right.
Next slide.
The next one, yes. Let me read. You are talking about this one?
Yeah.
Yeah.
I mean, maybe this was just your example, but in real world,
Yeah.
you can have a motion object moving,
Yeah.
but because the background is still the same, maybe like you might misconstrue the back part of the background as the image too. Like between the wheels, there's a piece of the road, right? And that could be misconstrued as the object.
Yeah, it's possible. Especially here, we have the shadows. So the shadow always moves with the object. So,
yeah.
That is something that is inherent, maybe. So it depends on how you define a shadow.
Right.
Shadow a part of the object, or it's a part of the road. Right?
Yes, exactly.
So
I guess I'm asking, like, are there unsolved problems that you could?
if there's so we are talking about this liberation model. Remember, like the consistency between the frames. And in this case with shadow, the liberation assumption is broken. The next image can no longer be reconstructed by the previous image here because there's illumination change. Yeah, think about this.
Okay.
Yeah. So there's some issue here for sure. But the empirical results are okay. So look at this result. Actually, the shadows are segmented.
some part of the.
Yeah, some of the shadow is 70. Yeah, here, right, this one, the shadow is 70, yeah.
Right.
Yeah.
But do you see, like, for example, some different kind of training where you can have that contextual data as well? Like, let's say you have two objects and both have
Yeah.
the same background. Like,
Yeah.
could you use that to solve this problem or?
I think for longer term, for example, this one, we can get the shadow removed.
Yeah.
Because look at this background, right? There's no shadow there. So technically, we can just distinguish this maybe a little bit. But in principle, I think it depends on how good your motion estimation model is. If the motion estimation model can distinguish what is shadow and what is an object, then that's fine. Otherwise, I think the shadow will always be included in the object.
Have you ever toyed with applying any of these techniques for CAPTCHA solving?
For
You know, like CAPTCHAs on the internet, like you're logging into Google and you get an image and you need to identify, I don't know, streetcars.
I see, yeah. So we didn't try that, to be honest. So because that one is about aligning the symbols to the object. So what we are solving is like trying to find the objects and aligning the symbols, then we leave it to these vision foundation models. But we do use captioning for here.
I'm talking about CAPTCHAs. So like, you know, when you log into.
Oh yeah, the captures. I see.
The type, this is a.
Yeah,
card.
okay, I got it. No, I think we haven't tried that. I think we should try it on this.
But
like,
it's Google
augmented.
Capture that use one single static image.
There's different kinds.
Yeah, if it's moving, I will assume that there's something we can do. There's something we can do.
Yeah,
But even
there's
if
some new kind of captures.
Oh,
that are
they're new?
moving up.
Yeah,
I see that.
If there's like this moving background things, then there must be something that we can do.
But that would be like,
Everyone
that would be
hates
very,
Cool.
that would be an interesting security paper.
I think
So,
I think that's
So one of the biggest or most impactful things I see here is the piece where you're describing you could use the motion detection model and bootstrapping mechanism to basically do object extraction. Have you guys attempted to kind of do this on a large scale and build like a new, more comprehensive object?
That's what I'm running right now in my computer.
Is it?
Yeah, that's what is running in my computer.
Great talk, by the way. I'm really interested in this idea of using motion to kind of fix everything because it adds a new dimension. So you don't have to think about it, things like that. But I'm wondering how much does the quality of the inputs affect the segmentation? I would assume that it does mitigate some of that.
Yeah, of course. So the most important thing about this is it affects the accuracy of your motion estimation.
Right.
Once we get the motion field right, then it's okay. Yes, but if we have low quality input, let's say if there's illumination issue, for example, shadow, right, we just talked about, then that will have some effect on the final accuracy.
Sort of related to that, when you use the bounding boxes to extract the objects after identifying them. Did you ever have to use like super resolution to create better images?
Oh, no, we just take all the bounding boxes.
So it's just one frame.
Yeah, so we don't need to do something about super resolution. So I think the one you are talking about is here, right? This one.
Yeah.
So we just take whatever is in the frame,
so how well does this work if you have, like drone footage?
Like a drone footage?
So if you have a drone that's
Yeah.
flying over things.
Yeah.
So the entire camera is moving constantly. And the objects are moving.
Yeah, I think the drone thing, my first comment is it's more related to the geometry part. Because we want to get the geometry, the landscape of the things, right? So I think if we
But what if you have animals moving, and you have cars?
that works.
But also the camera is moving a lot.
Yeah. So all these things have
So
moving
here
camera.
it seems it's
Yeah.
only fixed camera.
Yeah, look at the one in the back, it has moving camera. So
The blue one.
I should have shown more results with moving camera,
Yeah,
but yes.
but it's not moving like
Quickly.
it's not moving like a drone, right? That's what I'm trying to say.
For example, this one.
No, you should have some consistency between two frames. Otherwise, if one object is out of the
So
image,
as long as the motion can be estimated accurately, then this thing will work. And then with the drone, we have additional sensors, right? We have the the speed sensor. If we can solve it not only by programs, but we can also solve it by the sensors. For example, we know the speed of the drone, we know the height of the drone. These are all the priors that
Or
we can
maybe
use.
the other way, like how many consecutive images you need, like two or
For this one, we need a whole video, and
How
for the
long,
next
like-
one, we just need 2 images.
2 images?
Yeah, so it's 30 frames per second, then it's very, very fast.
Okay.
Right.
So for the car moving, to detect just like its motion, for example, just like to get speed, do you need a depth sensing camera or like the 2 cameras?
For this one, we're not getting any speed. So we're just using this optical flow method to extract this vector field that is finding correspondence between the images. But if we have the camera calibration and if we have this sensor information, then we can estimate the speed of the object.
You said something about 2D mapping. Is that from 3D to 2D?
This one is like 2D. So this one, we did everything in 2D. Like for example, this one, we didn't measure the globe in 3D, but we just map it to a 2D thing.
And my final question, so if you have like a fixed camera,
Yeah.
and then there's like a car like moving across the,
Yeah.
would that be 1D since like the car is like moving across the x-axis, like it's not changing with damage? Would that be like 1D?
That is still called 2D because the vector is pointing, it's a 2D vector, is pointing to the right side. Right. It's just not pointing to this side. So this direction, the value is 0, but it's still 2D. So the vector is always 2D.
Just one final question. Have you looked or thought about how you might apply this to some of the event-based vision cameras?
Yes, event camera is something that we are interested in. Right? So what event camera does is look at the difference between 2 images, right? It's gated at 1 or 0, for example, right? So we're always trying to think about event camera this one. Yeah, for
I've
sure.
got one in my lab. This would be very useful.
Yeah, for sure. Yeah, this is something we just talked about like weeks ago. If this generalizes to event camera, and I think it should. No more questions?
Are there questions online? Hey,
I want to stick in one more question.
Oh, yeah.
Following on what I mentioned. Considering the quality of the input does impact the motion model. Like,
Yeah.
figuring that out. I'm wondering if frame generation can be used to artificially improve the quality of the.
Oh yes, that's a big topic. That's a big topic. So nowadays, Sora, you guys, I assume that you know like Sora video prediction, right? And using video prediction as a generic pre-training task is a very hot topic. And there is reason why. Even people doing video, sometimes they don't know why they do it. They say, oh, it works. So for me, if I'm here, I want to predict my next video. What do I need? The first thing I need is 3D perception. So if I know the 3D, if I walk, then I will know how to map them to my next frame. And this is geometry. And outside geometry, what is there? Moving objects, right? If there's no moving object, then just with geometry, I can map things. So solid motion, and there is motion here. And the last piece of things is something does not exist in the first frame, but will reveal in the second frame. It's occlusion here. Yeah, so that's why you can see we are dealing with like motion, geometry, occlusion separately. Well, if you give me like $1 billion to build a cluster, then I will directly train on the video generation. That is true, right? But this is the principle. This is the principle.
Maybe you have any questions?
No, I think that's it. Thank you very much.
Thank you. Thank you.